The last question on this readiness check asks you to solve a system of linear equations. It's 4x minus 8y equals 12, negative 6x plus 12y equals minus 18. So I suppose I should ask, first of all, what has been your overall strategy so far? Like what methods have you been using to try and solve these systems of two equations with two variables? So I really appreciate that we heard from 3 or 4 of you, and each of you had a different perspective on how to do a question like this, and that's good. That's healthy. Some of those perspectives. So Peter, you tried a matrix computation with a calculator. You plug that computation into a calculator, and it's going to sort of choke on this one.
Yeah, it did.
Yeah,
Yeah. Mhm.
and so that is an interesting outcome that later in our course we'll come to appreciate why that might have happened. Because yes, trying to do this calculation as a matrix calculation is going to run us into trouble because the matrix that we would define in order to do this calculation ends up not being an invertible matrix. It's not a matrix that we can divide by. So it kind of has that same problem as the real number 0 has. We can't divide by it and get a reasonable answer. So as a matrix calculation, this particular problem doesn't work so great. We could take a graphical approach. This was some of what Helen was describing. If we graph both of these equations as lines in the xy plane, we can use the relative position of those lines to tell us how many solutions that this system might have. So that was a lot of what this first readiness check was about, where if we have two lines that intersect in a unique point, that unique point is going to be the single solution of the system of equations. If I have two lines that are parallel to one another, by definition of parallel, that means that they don't have any intersection points at all, and so there would be no solution to such a linear system. And then there's this example. And in this example, if you graph both of these lines, you find out that actually they are incredibly on top of one another. That every single point which is on one of these lines is also a point on the other one of these lines. And so graphically speaking, we get this sort of confirmation that this system has infinitely many solutions. But then you also mentioned, and this is the perspective that I want to kind of pick up on here, that if we were trying to do this algebraically, one of the methods that we could use is the method of elimination. And usually in the elimination method, what we try to do is add the two equations together in such a way that it will cancel out one of our variables, right? So we try to get the coefficients of either x or y to be equal and opposite, so that if I add those equations together, that coefficient will cancel out, allowing me to solve a single variable equation for whichever variable remains. So if I try to do that in this example, I'm just going to use this little Desmos tool, which I'll share with you if you're interested in playing around with it too. I'm just going to paste a link into the chat. So I can use this little slider here to multiply my first equation by whatever, right? So if I multiply my first equation by 5, then I could multiply my second equation by -4. And if I added those together, that's not going to cancel one of my variables. So if I go back to the original, so here's original. What could we multiply these equations by to set us up to cancel out, to eliminate one of the variables?
3 on top, 2 on bottom.
Right. So what we would be looking for is we want to find, for example, the least common multiple of the coefficients of x, let's say. And the least common multiple among 4 and 6 would be 12. And so we figure out what do we need to multiply by in order to bring each of those coefficients to a 12. And so for the first equation, if I multiply it by 3, that gives me a coefficient of 12 up top. And in the second equation, multiply it by 2, that gives me a -12 on the bottom. Right? And so when that happens, I add these two equations together. And not only does the x coefficient go away, but the y coefficient goes away too. And now I'm realizing that I have a problem with this little applet. Let me just go fix it real quick. All right, I got that all fixed. And Desmos is still thinking about saving it for some reason. I don't know why it's dragging its feet. But anyway, when we multiply this first equation by 3, the second one by 2, we add them together. Not only do we succeed in canceling the x's, we also succeed in canceling the y's. And so the first thing that tells me is that the values of x and y no longer have any power to determine how many solutions this equation has, right? Because the new equation that we get doesn't even have an x or a y in it. So the thing that we get is either going to be a true statement independent of the values of x and y, or it's going to be a false statement independent of the values of x and y. And that all depends on what we get on the right-hand side. On the right-hand side, we got 0. And so when we add these two together and simplify, we just get 0 equals 0. And so that's a true statement no matter what values x and y had in these original equations, right? And so what that's telling me is that any x and y which meets one of these equations standard will also automatically meet the other one, right? So that's telling me that these two lines coincide with one another. What might I change about the original problem if I wanted to get a situation that had no solution? What would be one thing that I could do differently here if I wanted to create a system that had no solution at all?
Could you change like the right-hand side?
Okay, how should I change the right-hand side?
Just make it a different number.
Yeah. So on the right-hand side, I don't know, let's maybe make this 18 instead of 12, right? Just pick a different number there. And now if I do the same scaling, because I have the same strategy, right? I want to cancel one of my variables, and so I want to make the coefficients equal and opposite. So if I do the same scaling as before, my x's and my y's are still all canceling, but my right-hand sides are no longer adding to 0. They're giving me this phony 0 equals 18 false statement. So what that's then telling me is that the values of x and y that satisfy both of these equations would also necessarily be compatible, their truth would be compatible with the statement 0 equals 18, which in our typical real number system is not a true statement. And so what that means is that there is no x and y that satisfies both equations, because if there were, we would also have to accept the assertion that 0 equals 18 is true. So as long as we don't accept that assertion, there is no x and y that satisfy both of these equations. If you ever do linear algebra in a fancier context, like over finite fields, which you might do in a cryptology class, then you can bend those rules a little bit. Because in a cryptological situation where you're working over a finite field of characteristic 3, for example, the number 18 is actually not distinguishable from 0 in that situation. And so this system might not be inconsistent if we're working over a different number system. But over the real number system that we all know and love and believe that we understand until we take a course in real analysis, this is not something that will have a solution.